Hello everyone and welcome to the EMS webinar, motor design webinar. Today we're going to be talking about a brushless DC motor that I've prepared here to present in this webinar, and through this we'll be able to show you how EMS is capable of handling motors and motor related questions, motor design related questions. So we're a fully embedded array inside SolidWorks. You just want to make sure that EMS is the EMS array is active. This way we actually save you the trouble of having to go through importing, exporting, transferring between softwares, and all the problems that come associated with that process, from having to deal with non-native parts and not having the flexibility of actually editing and modifying your design, your model. So here for us at EMWorks, our mission is to make to make electromagnetic design as easy as possible. And so what we did is we brought the electromagnetic simulation, the electromagnetic solution, to the SolidWorks environment. So here you see this is the CAD tab, the SolidWorks CAD tab. Yes, I believe most of you are SolidWorks users, and so you know you're familiar with this tab and you use it all the time. Now what we added with EMS is this tab right here. So anything you build inside SolidWorks, EMS is going to be able to automatically see it, and you can set it up and analyze it on EMS with minimum effort. So the first step in an EMS study is in an EMS design is to create a study or a design scenario. So you have 5 solvers that you can choose from. You have the magnetostatic, the electrostatic, the electric conduction, the AC magnetic, and the transient magnetic. Depending on the application, depending on what you're trying to do, you would decide which one of these you want to use. So you got the magnetostatic if you're dealing with a model that is excited using DC current or permanent magnet. Electrostatic if you're analyzing the electric field generated by DC current or voltage. Electric conduction is the model for studying the conductivity of your structure. AC magnetic, and if you have coils excited with an AC current, and so you get to specify the frequency of your current. And then transient magnetic covers every other kind of current, so being pulse, a step function, anything that any kind of current. You can even import current versus time curves in there. So because transient magnetic goes over a time span, so you got start and stop time, and then it breaks it into steps, and at each time step EMS is going to acquire the value of the current and use that as the source, and so with that you can actually do any kind of current there. We have also 2 extra modules, the steady state thermal analysis for those of you who are interested in studying the thermal behavior of your design, the Joule heating, the temperature generated by the excited coils. And also we couple to motion, so any motion you define inside SolidWorks motion, we'll be able to couple to that and analyze it for you, and we can tell you the effect of your motion on the electromagnetic behavior and vice versa. So now creating a study, you have this manager tree right here. For those of you who are familiar with SolidWorks simulation, you realize here that you probably noticed by now that the EMS manager tree is very similar to that of SolidWorks simulation. Sorry. And that's one of the reasons why we're gold certified partner of SolidWorks, because we feel and look just like SolidWorks. So for SolidWorks users who do not know that EMS is a third-party software, they would think it's a SolidWorks product. It feels and looks exactly like SolidWorks. Okay. Here we have all these steps, these icons. So you got solids. This is where you define the material for your component. Load restraint for defining boundary conditions. Coils for obviously defining your coils. Forces and torques for studying the force and torque on certain components. And then meshing. Solids, again, as I said, defining material, very easy. We have a very rich material library that you can choose from. If you have a custom material or if you want to modify certain materials, EMS allows you to create your own material library, and inside there you can actually create and edit any material you want to add, and you can save that so you can use it in other projects as well. So here, for instance, let's say we take neodyme there. Yeah, in material assignment, we can drag and drop to copy paste if we have two components with requiring the same material, and we can also multi-select. So assign material to all of them at the same time. Okay. Load restraint, basically, if you're interested in thermal, this is where you get to define your convection. And the convection is defined on the outside air of the structure. So you specify the ambient temperature and the convection coefficient. And since we're talking about the outside air, it is important here to note that every electromagnetic simulation has to happen within an air box. Now the reason for that is unlike mechanical structures where most of the stress and strain, actually all of the stress and strains happen in the structure itself, in electromagnetic simulation, a significant portion of your fields are actually propagating in the air surrounding your structure. And of course, if you want to capture that field and take it into consideration for your design to be accurate, you need to model the air surrounding your structure. And so it's very important that you add an air box inside SolidWorks. You add an air box to your design like this one right here. Okay. Sorry. Coils, we have two options, solid coil, wound coil, depending on what kind of coil you're using. And this is another advantage we have is you do not need, if you have a wound coil, you do not need to go inside SolidWorks and actually draw all the 50, 60, 100 turns of coil, whatever you have. All you need to do is draw the overall envelope, specify the AWG or the diameter, the input port, the output port, number of turns, let's say I have 300 turns or whatever, and then the amount of current per turn. Forces and torques, basically if EMS automatically computes the force density distribution on all the mesh nodes. However, if you want to study the forces and torques on a particular part, you need to select that in here. So basically, in this case, I'm interested in the torque on the rotor. So I can actually select that there and then just say yes. And then the last step is the mesh, and the mesh, this is where we really stand out compared to competition. Because mesh is always the bottleneck of your simulation, and when you're meshing, you're interested in precision and speed at the same time. And in most softwares, they make you come to a compromise between precision and speed when it comes to the mesh question. In EMS, you don't have to do that. We give you the mesh control option, which gives you the best of both worlds. Basically, the areas that you think are critical and important, you can select them and do a very fine mesh there. The areas where the mesh is not that critical, you can relax the mesh constraints there, so you can actually compensate for the extra elements you create, and that way you have actually precision where you need it, and you have fast simulation. Now, once you mesh your structure, this is how it looks like. Okay. Now, after meshing, you hit right-click here, you right-click here, and you hit run. After running, EMS will generate these result folders for you. Okay, so now we're done with the pre-processing. Now we're going to get into the post-processing part. And so here the motion results table has all the lumped quantities, the force, the torque, back EMF, resistance, inductance, flux linkage, energy. Let's say here we're interested mainly in the torque, and again, because we're coupling to motion, we have at each time step the values are varying. So at each time step, EMS is actually recomputing everything. So here, let's say the torque around the z-axis. This is the variation of the torque. You can use a cursor to read that. The values are right here. You also have them in a chart here that you can save as Excel or TXT for any further processing. Same thing could be done with the back EMF. You can again use a cursor to read the back EMF at each time step. Again, you have them all in chart here that you can save as an Excel spreadsheet or a TXT file. You can use them as an input for in any other software. Same thing could be done with all the other quantities as well. Then we have the magnetic flux density, the magnetic field intensity, the applied current, and the force density. These four quantities, they could be plotted in 3D format. We also have the flux, so you can compute the flux through any surface that you choose. So magnetic flux, for instance, now whatever I'm going to do here for the magnetic flux applies to the magnetic field intensity, the applied current density, and the force density. So everything I do, all the manipulations I'm going to make here, they apply to all of them. So we can do 3D and 2D plots. For instance, if we go for 3D, we can choose the component X, Y, Z, or the resultant. The unit, Tesla or Gauss. We can choose whether to have fringes or vectors. So let's say if you want to see the vector lines, you choose vector. And you can choose which time step, because remember we're coupling with motion. So at each time step, we can actually plot our magnetic flux density there. So now, as you can see, you can actually see here the flux lines. Okay. Right. So you can actually manipulate that, and you can see all the flux lines right there. You can change the chart option if you want to play with the scaling. For instance, so now let's say I want to focus more on what's happening here. I can change the scale because usually in the same structure, when the areas with very high values tend to shadow what's happening in the areas with low values. So I can play with EMS. You have the flexibility of modifying the scaling so that it actually fits. You can see more and focus more on the areas with small values if you want to do that. So, or you can just go back to going with minimum and maximum on shown parts. You can animate, because we're associating with motion, we can actually animate and tell you exactly as your rotor is rotating, what's happening to your magnetic flux lines, magnetic flux density. So as you can see here, the values are varying and the arrows are changing, adapting as the rotor rotates. Okay. You can also use the vector plot options here. So let's say I want to reduce the density here so I can get a better view. I can go, let's say, for an 80% density, and so reduce the vectors. I can change here the size of the vector, of the vector lines. So it's very flexible there, and it we can also do probing. Basically, probing, you can click anywhere on the structure. EMS will display the value for you at that position. All the probe points that I clicked at are stacked right here in a chart with the XYZ coordinate of each probe point, the field value, and the node number of the mesh. We can plot these points, and you can save them as an Excel or a TXT file if you want to go further with this. We also have the option of listing. Basically, listing gives you every single node in your structure with the XYZ coordinate of that node and the value at that node, and the node number as well. Again, this chart can also be exported as an Excel spreadsheet. You can also, instead of vectors, you can decide to do a fringe plot so that you can get a scalar representation of the magnetic flux density. Again, you can still manipulate the chart option for better contrast. Or you can just decide to go back to the minimum maximum. You can do section clipping. Basically, cut through the structure and look inside to see what's happening within your structure. The cut plane, you can drag it with a mouse to any position. If you have a particular position in mind, if you don't want, let's say you don't want to drag it with a mouse the way I'm doing, if you have a particular position, you can actually type that. You can tilt the angle of the cut plane. Sometimes that is needed for certain structures. So now you can look at it here. You can see the angle there. It's not 90 degrees anymore. You can change the orientation of the cut plane. You can do an inside out to decide which side of the cut plane you want to display. You can do plot on section only, and that's going to do the plot only on the cut plane. It's a planar plot there. You can superimpose more than one section clipping. You can go up to 6. Okay. You can also do an ISO clipping. Basically, ISO clipping will take all the spots in your structure that have equal value, and then it will plot those for you. Now you can decide on the value that you want to plot by dragging this cursor right here. And again, you can superimpose up to 6 isoclipping surfaces. This is very handy when you're looking for your minimums and maximums for design consideration. So I can locate, pinpoint where my maximums are. So I know here my maximums are at these two spots right there, the yellow ones. Again, as I said, you can go for up to 6 isoclipping surfaces. Also, you can do the probing like the one I showed you earlier with the vector. Same concept. You have the XYZ coordinate of each probe point, the field value, and the node number. You can animate that as well. And you see here where it says play to file, so you can actually save this animation in a video file, AVI file, that you can actually use later on in presentations or on your website or anything. You can save all this in a video. Okay, right. So also now you might wonder, okay, I want to see numeric values. I want to see what's happening numerically, because that's what engineers care about the most, is like how much flux I'm getting, and how is my flux varying from one point to the other. And that's where for that reason we have for you here the 2D plot. Basically the 2D plot, it's going to ask you to specify 2 points. For instance, let's say I select these 2 points. EMS will go, and by the way, I can select any 2 points on the structure. I just selected these 2, but you can select any 2 points in your structure. EMS will go along the straight line connecting those 2 points. It's going to split it into the number of samples that I specify right here. And when you hit it, okay, it's going to plot the magnetic flux density along that line, and you will be able to see numerically how is that varying. So you have a cursor here where you can read the value at any positions. The values are being displayed right here. Again, you have it in a chart here. You can save as an Excel or a TXT file. You can also, what you can also do now, same thing could be done with all the other quantities as well. Let's say, for instance, I just thought about an idea and I want to measure what kind of flux I have a little bit above my structure. So what I can do is I can take this plane here, insert a reference geometry, a plane that is parallel to that, and then I can decide how high up, let's say 10 millimeters. So if I want to see what's my magnetic flux density 10 millimeters above my rotor, I can use that plane as my base. Okay, so let's say, for instance, along this circle right here, how is my magnetic flux density varying? So I can use that sketch, and I can insert points there. So you see the purple points are the points that I've inserted, so I can go for more points if I need to, or less. Okay, so it's adding those points for me now. And then what I can do is I can do a 2D plot there where I import all of those points just with one mouse click. Okay, and then I can plot. So now I can see how my magnetic flux density is varying along that contour that I selected. And I can use again the cursor to read my values, and I have them in a chart here that I can save as Excel or TXT. Okay, as I said, the same manipulations could be done with all the other folders as well. Also, now let's say I want to start. I've had my original design, and now I want to optimize a little bit. So let's say I want to see if I use, for example, in this permanent magnet here, I used neodymium. These magnets, I used neodymium 42. Let's say I want to use neodymium 52, for instance. I do not need to go through the process again. All I have to do is drag and drop the study, give it a new name, say neodymium 52, and then say yes. Now what happened here is EMS copy-pasted everything for me into a new study. So now I can do any modifications I want to do in here without affecting the results from the other. So everything now that happens here does not affect what happens there. So I get to keep my old results and play around with the new ones. And for instance here, I said if I want to modify my material, or I can modify my current, whatever parameter that I want to modify, I can come here, say yes. Okay, now as you notice, the results have been grayed out. Now all I need to do is right click and hit run. And EMS will automatically now run only this study, and for that kind of using those parameters. And then I'll be able to actually compare results. Now I can also do something else. I can do a few of them, whatever modifications I want to make, and then I come here and say run all studies. So if I'm trying to optimize and sweep something, I can use that feature right there. And I've done here actually one thing. For instance here, if I go on the magnetic flux density, I want to compare what happens now if I want to see the difference between using neodymium 52 and neodymium 42. I can do a 2D plot. I can ask it to go from here to here, take 200 samples, and then I can say compare results. When I compare results, I have a list here of all the studies that I've defined that I can compare with. And EMS will actually superimpose both plots on the same figure. As you can see, the red one is the neodymium 42, the blue one is the neodymium 52, and you can see exactly what kind of variation, what kind of influence that is going to have on your desired outputs. And again, you have them in a chart here, both columns, that you can save as an Excel spreadsheet. You can also compare, for instance, the force or the torque. So okay. So yeah, you can actually compare those, as I said. So you can see the variation as you change your magnet. Okay, so those are the comparison there between the studies, and we can keep doing this. We can also, another feature that we can take advantage of, another SolidWorks feature we can take advantage of is the isolate and the hiding. So for instance, I want to see just the magnetic flux density on my rotor. Okay, so I want the scaling to automatically adjust to what's on my rotor. I can isolate that, and then when I come over here and double click, it's only going to plot that for me, and it will automatically adjust the scale so that it fits exactly the minimum and maximum on this piece right here. And again, I can do all of the other manipulation. Let's see if I can animate so I can see just this piece as it rotates, what happens to my magnetic flux density. I can also do section clipping in there. So I can cut through my piece, see what's happening. Okay. So any pieces we show or hide, the plot will automatically adjust to what is being shown, and that way we can manipulate that and change our display and have different plots for different pieces. That would be very handy for us. We can also take advantage of the multi-configuration feature of SolidWorks. So if we have several configurations, we can actually modify them and associate studies with configurations. So just the way I copy pasted here for changing the neodyme, I can make exactly the same thing by doing several configurations and actually associating. As you can see here, if I copy paste, it's going to ask me here the SolidWorks configuration to use. So I can actually, if I had several configuration here, I can choose among those. And at the end here, for instance, let's say after I've generated all these plots and all these figures, eventually I'm going to have to share this data either with colleagues at work or with clients or anything. Instead of you having to go in and copy paste every plot of your structure, EMS actually can do that for you. Again, we want to make your life as easy as possible, and we go through a great deal of trouble to make sure that you have the easiest experience and the smoothest experience possible. So through the reports feature, basically you can select which section to include, which sections to leave out. You can upload a company logo. You can put the author name, the company, the date. You can choose the format, HTML or Microsoft Word. And as soon as you hit OK, EMS will actually copy paste everything for me. From the plots into a nice Word report compiled all together without me having to actually go through the process of copy pasting each and every one alone separately, because that tends to take a long time. Okay. And at the end, this is how my report is going to look like. So I have my logo there, I have my study, the date, I have the model, all the material properties right there. Then I assigned all the pre-analysis setup that I did right there, and then the study property, And I have also the result table. All of those tables are right here. So the forces, the torques, the resistance, all the result tables are there. And also I have all the plots that I've generated. They've been copy-pasted, automatically copy-pasted for me. And the advantage of this is that this is a Word report, so anyone can view it. They do not need to be they do not need to have SolidWorks license or EMS license to view it. Anyone with Word can view it, and you can actually put up this on your website, convert it to a PDF file, take figures from the report and put them in a PowerPoint presentation. So literally there is no limit here to what you can do with this. There is also another example here I wanted to show about motors, is because to show you in the case if we use, because here we used magnetostatic, we assumed we have a DC current. Let's say you have any other kind of motor, and and you're actually not exciting with a DC current. You're exciting with some square function current, or some random current that you're using. So just going to show this example here. Okay. So this is an example that I have using it's a reluctance motor. Okay. And I've defined here using yeah. Okay. So what I did here, I used the transient magnetic analysis, and I coupled it with motion. And with the transient magnetic, there is this feature here when you're doing the sign on the coils. You have all kind of option here. So if you're doing a coil, you can excite using a DC, you can excite using an exponential current source, a pulse, SFFM current source, sinusoidal current source, or another feature is import a current versus time curve. So if you have a curve that is already defined, you can actually import it, and this is how it's going to look like. For instance, here I have the step function here I'm using to excite my coil. There is no limit here to what you can import, and you can use any kind of current to actually analyze your structure. Okay, so again here you can do whatever you need to do, like is the plots here too. We can plot them there. We can animate, we can do section clipping, just like we did with the magnetostatic. We can do the same thing with the transient magnetic. So you actually have no limits here to what you can do. It's very flexible, very easy to use, very user friendly. And so again, it's very flexible here, and you can use this to optimize your design to okay. And again, as I showed earlier, we can animate this And we can show it. Actually, what we can also do is we can plot at each time step. Okay. So it's still loading a little bit. Yeah. So again here, as I change my coils and I change my excitation from one coil to the other, we get, actually we can push the rotor to rotate. Okay, so now I'm going to open up the floor to questions. So if you have any questions, please feel free to type them in the chat box right there. Yeah, about anisotropy in the core. So yeah, we can actually here in defining the material, as I mentioned earlier, EMS actually gives you the flexibility of defining your own material if you want, or and so we can do isotropic, orthotropic material, lossy isotropic, lossy orthotropic. So you can actually define that. It's very flexible in that regard, and you can modify it and define it any way you want. So it's a feature that you can add and you can do here in the when defining the material. So that's something, yeah, EMS does handle. Yes, with the other question is with an applied current in the transient solver, are the effects of inductance on the current calculated? Yes, we do actually calculate the effect of the inductance. Okay, let me. Yeah, that inductance is calculated, and we can actually predict that for you, and we can display it in the results table. So one of the tabs here. So one of the tabs in the results table does cover the inductance of the on the coil. Another thing here in defining the material, just another way to show you also the flexibility of EMS. When you're defining material, EMS actually can even take nonlinear material where you can import your own BH curve. So for instance here, if, you can import it as a DAT or a TXT file. So here, if you have a BH curve as a TXT file, you can actually import that into EMS and actually use it to modify to define your material. We also have in the built-in EMS library. In the built-in EMS library, we actually do have nonlinear material as well. So for instance, steel 1010 or any other type of nonlinear material could be covered in there. Okay, we can also, for instance, if you want to see if you want to see the magnetic flux density in the air surrounding the structure, what you need to do in this case is to, right here I've hidden the air box, but you can actually display it. Because again, as I mentioned earlier, every electromagnetic simulation has to happen within an air box. So if I make it transparent there, so if I include that and I do my magnetic flux density, I can display the fields in the air surrounding the structure. Okay, so everything is included and I can see it in the air as well. Does Okay, there is another question about the air property and the air gap. Basically, the way we introduce it is we just built the air shape in SolidWorks, like this one, as you can see here, and also obviously that automatically will cover the air gaps, or we can even build a separate air for the air gaps. And then when we go here for the material, we do amongst the many things that material library has, it has an air component. So if you apply air to that piece, it will automatically know and recognize it as air and would treat it as such. And also another question about the phase in the motor. We treat we can do single phase motors and we can do multi-phase motors. So we're not only limited to 3 or 1. Whatever number of phases you need, you can introduce that in EMS. So if you have 6 coils and they're let's say 30 degrees away from apart, lagging, each one is lagging the other, let's say 30 degrees or whatever, 40 degrees or whatever phase you have, you actually will be able to introduce that and modify and model it exactly, so you get to set up the phase and the amplitude of each coil separately. And so if you have multi-phase structure to analyze, you can actually do that. And another question about, does EMS interact with simulation? What we can do with EMS, as I showed you earlier, we can give you the listing of all the values. So every single node of your mesh structure is in that chart, and then you can use that as an input in simulation or any other software. Okay. Any other questions? The other question we got here is, do coils have to be connected, or it can be just something that simulate the coil? Yeah, actually, and yeah, as I mentioned earlier here, for instance, the coils do not have to be connected. What you need to do here, let me show you this, what I have here and what I've done. Here you define the coils. Okay, just okay. So what you can do here, you can define the coil the way I'm doing here. I'm just going to isolate it for a better view. Okay. So this is how you need to define your coil. Okay. So this is it. You define the overall shape. You define the overall shape of the coil, and then basically when you go here, you choose it as a coil. Okay. Yeah. Do a new study. You choose it as a wound coil. So here you have two options. You have the solid coil and the wound coil. So if you select this as a wound coil, you set up the AWG, or the diameter of the wire. You set up the component that's going to be your coil, for instance this one. You can do the input port. Okay. And this is a loop coil, so you can do the output same as input. So now you have your currents going in a clockwise direction, and so you do not need, yeah, I know it's it's hard to actually draw all the details in SolidWorks. You do not need to do that. So just draw the overall envelope, and then select it as a wound coil. Set up the number of turns in here, whatever number of turns you need to they need to be, and then choose your current type: DC, sinusoidal, imported current versus time, whatever you need to put in there, and then you define it like that. The other question is, does EMS use the induced current in the core to calculate the overall field? Yes, it does, and it takes that into consideration, absolutely. Okay. Okay, another question is how to set particular corrosivity direction in a magnet. Okay, that's a good question. For instance, here, I'm going to go back to the other model so I can actually show you that. It's very easy, very intuitive, straightforward. Just a minute here until the coil loads, the model loads. Okay, so for instance here, if I go back to the original model that I've shown, if I isolate this magnet, so I want to set up the corrosivity of this magnet. Okay, what I can do here, I right click and it says here corrosivity direction. Select that. Now if I look here, the red arrow there is my corrosivity direction. Now I can choose to have cylindrical coordinate the way I did in this model. I can have Cartesian coordinate. In certain cases you might need to have Cartesian coordinate there. I can decide on the axis. I can do positive, negative. I can do local or global coordinate system. So it's pretty much covers everything there. So it's very easy, and then you just hit OK, and your magnet is your magnet's corrosivity is taken care of. Okay, any other questions? Okay, how to play with the dimension of the motor example, the gap, without building a new assembly. All right, this is the multi-configuration feature. I'm gonna quickly show I'm gonna quickly show an example here that I have. Okay, this is an example of a solenoid, but I mean the concept is the same. So we have here, through the multi-configuration feature of SolidWorks, I can change any parameter or any geometry of my structure. And then I can come over here to SolidWorks, to EMS, define a study, let's say for this configuration, then copy paste it, and let's say call it config 2, and then here it's going to ask me with which configuration to use it. So I can choose here, let's say the other configuration that I set up. So automatically now the solver went to the new configuration, and now all I need to do is right click and hit run. The solver will automatically remesh and rerun it for me, and I can compare results. Let's say, for instance, if I want to see the magnetic flux density from this point to that point, and I want to compare between this study and that one, the other configuration. If I hit OK, now I can see the effect of my geometry variation on my results. And I have them here in a chart again. So I have them both superimposed there. So you can actually do as many configurations as you need. With each configuration, assign a study, just copy paste all of them, each to one configuration. Then you can right click and hit run all studies, and it's going to run them all for you. Yeah, if you put, because in the here another question about the torque. Is it being calculated, the torque in the shaft, is it being calculated just due to the induced current, or to the also the inertia? Now, because we communicate directly with SolidWorks motion, so if you put some sort of torques or inertia there in SolidWorks motion, EMS will interact with it exactly, and it would tell you the net torque. So you'll be able to predict actually whether or not your piece is going to be moving or not, and all that. Okay, so I'd like to thank everybody for attending today. It's 3 o'clock now, so thank you for attending. It was really a pleasure having you and answering all your questions. I hope I was able to address all your issues and your concerns. So thank you for attending.
I would like to add, Bill, just wanted to thank everybody for attending this webinar. Starting from tomorrow, we'll post this webinar on our website. So, gentlemen, you can always go back to our website and download the video of this webinar, the session of the webinar, and you'll be able to find it on our website at www.emworks.com. How do we? You can contact. You can contact me personally, Adam at emworks.com. That is how you can contact me, sir, or you can call me by phone at 514-612-0503. And you can always go on our website and you can fill an inquiry form there. There is a download request, web demo request, whatever you're looking for. You can always, find us. Thank you all, gentlemen. You all have a good day, a good evening for some people, good morning for some others, and good afternoon for some others. And it's been a pleasure. And hopefully